Hello and welcome. My name is Sylvain Jeaugey. I am the lead developer of the Nickel library at NVIDIA, and today I will present what Nickel is, how it works, and why it is a key component when training deep learning frameworks on multiple GPUs. During this talk, I will be available to answer all of your questions on the chat, so if you have any question, don't hesitate to ask them there. The chat button should be on the bottom right of your web browser. Alright, let's get started. First things first, what is Nickel? Nickel is an inter-GPU communication library which is implemented in CUDA and which is designed to use your hardware in the most optimized way. Your hardware could be from a laptop with, say, 2 GPUs to a DGX server where GPUs are connected through NVLink, up to a cluster with thousands of GPUs connected through Ethernet, InfiniBand, or other networking technologies. There are many ways to get Nickel. You can download it from developer.nvidia.com/Nickel. It is also integrated in our NGC containers, together with the most used deep learning frameworks like PyTorch, TensorFlow, MXNet, etc. And finally, you can also get it from GitHub. The source code is available. You can recompile it quickly with a simple make command and 5 minutes. All you need is CUDA. Finally, if you ever wondering how fast your platform is, and whenever you suspect that Nickel could be the limiting factor in the scaling of your training, you should definitely check out the Nickel performance tests, which are also available on GitHub. All the numbers that I will mention in this talk about performance come from those Nickel performance tests. And in particular, we're using the bus bandwidth that those tests report, which is meant to reflect how much data is coming in and out from your GPU, and this is something that you should be able to relate to the bandwidth that your GPU should be able to maintain, be it using PCI or NVLink, or if you're communicating through the network, that should be related to your network speed as well. So as I mentioned, Nickel is a library, and as such, it is used by frameworks like any other library. They use it to manage the parallelism on multiple GPUs, and so it sits just below the frameworks and just on top of CUDA. All the frameworks, as I mentioned, support Nickel today. TensorFlow, PyTorch, MXNet, all of them. And so, yeah, it should be fairly easy to use Nickel within those frameworks. So now let's look at how frameworks use Nickel and how they use it to accelerate deep learning training. So first, let's understand how deep learning training works. So we have a neural network. That network has parameters, and our goal here is to make the parameters converge to the point where the neural network is doing what we want. And to do that, make it go through a database of lots and lots of samples. For example, in that case, it will be images. And we will make it go through a certain number of images, for example, 256. And after that, what we call a mini batch, we'll see how wrong we are and how we could improve our neural network to try to converge to what we want. So all those images will go through the neural network in what we call the forward pass. They will generate a result, and then we'll figure out how we can correct the initial parameters to provide a better answer. And that is done during the backward pass, where we compute the gradients. And the gradients are the same size of the parameters, and we compute them, and then we apply them to the parameters, which is basically when we learn. And hopefully, if we do that many times, or going through the whole database and going through that database up to hundreds of times, we can converge to the point where the gradients become small and there is no longer anything to learn. And obviously, going through a very large database hundreds of times takes a really long time. And that's why training some neural networks can take weeks or even months. And this is something that we obviously want to accelerate. And an easy way to do that is to use more than one GPU. So now let's see how we can do that. And it turns out that doing that is pretty easy. All we need to do is just split the batch between the different GPUs. Obviously, because each GPU will only process part of the data, the gradients well compute will not be what we should have had if we had the full batch. So each GPU will end up with a partial gradient, and there's an easy way to actually come down to the same result if we had the full batch. And the solution for that is simply to take all the gradients, sum them, and then get that result to all the GPUs, and they will get the same result as if they had processed the whole batch. And so that operation to sum all the gradients and then propagate it to all the GPUs is what we call an all-reduce operation. And it is what Nickel implements. So as you can guess, the more GPUs we have, the less work we have to do per GPU. So as we scale, the time to compute the forward and backward path will shrink, but the all-reduce operation will remain constant. And that means that to be able to scale to a large number of GPUs, it is extremely important that this all-reduce operation is done as fast as possible, because otherwise it will very quickly become most of the iteration time, and you can add more and more GPUs, it will no longer make your operation faster. And speaking about performance, it will vastly depend on the underlying technology you're using. Here you can see a variety of performance you can get depending on the platform you're running on. For example, if you use multiple GPUs within a system, just using the PCI Gen 3 by 16 link you have, that will give you something that will be around 12 gigabytes per second, potentially less if you're going through a CPU. But yeah, you won't be able to get more than 12 gigabytes per second. Moving to PCI Gen 4, you should be able to get twice that, 24 gigabytes per second at best. But even that is still way lower than what you would get if you were on a platform with NVLink. And NVLink can get up to 230 gigabytes per second, which is almost 10x more than what the PCI Gen 4 would provide on, say, an A100 GPU. If you plan to run on a cluster, same applies. The network you're using will be extremely critical regarding your performance. And if you start with a 100 gig card using TCP/IP, at best you would probably get 10 gigabytes per second, which is good for some cases, but not for all. And if you want to go further, you will need to switch to a technology that enables RDMA. So RDMA is great because it lets you read the peak performance of the NIC. Say 12 gigabytes per second for 100 gig NIC, with very little CPU usage. So it's very easy to get to that peak performance. TCP/IP is very quickly limited by the CPU. Creating packets, forming packets in the kernel is a big limiter here. So you really want to have RDMA there if you want to scale to 1, 2, or more NICs. And this is exactly how we design our DGX servers. Each DGX server has NVLink within the node, but then it has multiple cards, NICs between the nodes. And so DGX1 had 4, we moved to 8 with DGX2, and then we doubled line rate to 200 gig with DGX100, and that let us reach speeds that are close to 200 gigabytes per second of effective or reduced bandwidth, compared to barely 10 with just a 100 gig NIC. So let's look at the Nickel API now. This is pretty much an overview of everything that is in the Nickel API. There are a few more functions that are not that much used, but pretty much this is the core of it and what most code really use. So the first step to use Nickel is to create a communicator. And a communicator is just a group of GPUs that defines which GPU will be part of a group. And to do that, the first step is to create an ID. So we call Nickel getUniqueID, and then we'll propagate that ID to each GPU, which will be part of the group. And each GPU will call Nickel comInitRank on that, using that ID and using a different rank for each GPU. Then we also have a Nickel comDestroy function to destroy the communicator at the end. But we also have a way to get asynchronous errors from the communication operations if there's any error happening, or if the application decides that the communication is taking too much time, it can also decide to stop everything. And to do that, that would be using nickel-com-abort. And contrary to nickel-com-destroy, nickel-com-abort will also destroy the communicator, but it will not wait for all communication to complete. It will just stop everything right away. Then we have all the collective operations, or reuse, broadcast, reduce, rescatter, all gather. That are the most used one currently in deep learning. And followed by the new send receive primitives that we introduced in Nickel 2.7 this year. And finally, last but not least, the group start, group end functions, which are quite important to compose operations based on the previous ones, but more on that later. I explain why they're used and why they're important. Okay, so back to initialization. One very common question I get is, how do the different processes or different GPUs come together, connect together to create a group and a Nickel communicator? And so let's start by explaining how the bootstrap in Nickel works and how we initialize a communicator. So as I mentioned, the first step to create a Nickel communicator is to call Nickel getUniqueID. This is just done once, usually by one of the processes in the group, but not always. It could be done by some orchestrator that would then launch all the workers. So that's not necessarily the same, one of the ranks in the group. And so during that call in practice, Nickel will launch a thread that will be waiting for connections, and the IP port and address will be actually part of the unique ID, so that all the ranks can then connect to it. So that ID will then be passed to all the ranks by the application. Note, this is the responsibility of the application to propagate that ID to all of the ranks. And that should be using some CPU side communication system between one rank and the others, or between the orchestrator and the workers. Then all workers will call nickel-com-init rank, and each worker will call it with a different rank, from 0 to 3 in this case. They should always be different, and from 0 to n-1. And each rank will connect to the bootstrap thread, passing its own information, including its own IP port for further communication. And once the bootstrap thread has gathered all the information from all the ranks, it will then pass the complete array of information to all the ranks so that they can then connect to each other and communicate with each other. And then later on, during the rest of the nickel-com-init rank function, this mechanism will be heavily used to perform all the communication needed to establish connections, properly aligned all the protocols used, the algorithm used on the same size, etc., and make sure all the ranks can talk to each other to initiate the communication. It should not be used for high-speed communication later on. So this is just to set up things so that things are functional, but not for the real communication during the, for example, or reduce operation. So the bootstrap mechanism in Nickel relies on TCP/IP sockets to provide an out-of-band communication between ranks. It is not meant to be fast, just functional, but is running during the entire life of the Nickel communicator. And since, for example, for send-receive communication, we do not pre-connect all ranks to all ranks, and that will be done dynamically when there is a send or receive operation that is called, then we will connect those two ranks together. It also means that Nickel needs to be able to open sockets and connect to other sockets during the life of the Nickel communicator. And it is not a secure protocol. There is no security, no encryption, nothing like that. And so it is assumed that we can use a network there where we can freely connect between the different processes of a parallel job in a way that is not public in a way. So, for example, if you're running in the cloud, you should definitely make sure that you're using a private network for your job, and usually use Nickel socket ifname environment variable if needed to make sure we are using the right interface for that bootstrap. Okay, so that was the very first step of the creation of a NCCL communicator. It was an important step, but not really the most tricky one. So now let's look at the way NCCL communication works and, for example, how we perform an all reduce operation. So this is an overview of the NCCL architecture. First, we have a very advanced topology detection that will find where GPUs are, PCI switches, NICs, NVLinks, everything to know how GPUs are connected to each other and to the NICs if we are going to do some network communication. This step will build a graph representing the topology of the compute node, and this will be used on the second step, which is the search. So the search will look within the node and try to find how to maximize the performance of the collective operations and find optimal paths for different algorithms like rings or trees. And then it will also predict the performance of each of those algorithms to make sure we can tune things correctly to use the right one at the right size. The third step is to connect all those intranode graphs together through the network and to form the global rings or the global trees. And finally, when the application will run an NCCL operation, for example, reduce, we will launch some NCCL CUDA kernels to follow that path and make all the data flow from the GPUs through other GPUs through the network and perform the operation that we need to do. And those will follow the path that we just computed in the previous steps. Now let's look at each step more in details and give a few examples. The topology detection step will gather topology information from various sources, CPU information, PCI information looking into /sys, NVLink information through NVML, NIC information from the network API, and finally, NCCL can also get that information from a file that it can be defined by the user, or and that will provide the information in case that information is not available. For example, if you're running inside a virtual machine and /sys is actually not representing the true PCI topology, it can be useful to actually have an XML representation of that topology so that NCCL will be able to make the right choice in the next steps. Then once we have gathered all that XML information, we can actually dump the XML file. And if you ever want to report a bug, that's actually pretty useful to provide, because for us, that lets us investigate how the topology detection step worked and if anything is wrong there, and also even reproduce things more easily because we can check how algorithms work on those topologies. And then we'll derive from that topology the node graph, so the real graph for the next step. And you can see here a few examples of what the node graph will look like for a simple PCI topology, or DGX1, DGX2, or DGX A100. You can see how complex those DGX nodes are, the number of connections we have, PCI switches, NICs, there are a lot of things there. And it is extremely important for NCCL to get that right, because if not, the rest of the steps will be heavily compromised. And once we have that topology graph, we can try to start finding a maximum number of paths inside the node to maximize the bandwidth. Every path that we will try to find will start from the NIC, go through all the GPUs, and then exit from that same NIC. And at least that's what we try to do. So we try to maximize the network locality by making one flow enter and exit the node from the same NIC. If it's not possible, we might find another solution, but usually that's what we try to do. And we'll try to get as many as those paths within the node that can operate independently, so that we can all make them work together and aggregate the bandwidth from those different paths, so that we can get an increased network performance. And you can see here how NVLink is important for not just intranode performance, but even internode communication. If we didn't have NVLink here, we could not actually aggregate the bandwidth of multiple NICs because just one NIC would have a flow that would go through PCI and use all the PCI bandwidth just with one NIC. And it's only because we have an NVLink performance that can actually match the sum of all the bandwidth from all the NICs that we can aggregate that bandwidth and get an overall bandwidth which is way higher. You can see also that that bandwidth needs to be matched in the sense that if we had on a GXA100 16 NICs instead of 8, we wouldn't actually be able to get twice the bandwidth. There is a limit that is the intranode bandwidth, and we couldn't get, for example, 384 gigabytes per second on the GXA100 because the intranode part is limited to 230. And so this is why we usually try to match the network bandwidth with the intranode NVLink bandwidth so that we are not wasting any bandwidth there. Now let's look at how we connect nodes together through the network. So for rings, it is actually quite simple. We just connect nodes in a ring manner as well, so that the output of a node will go to the input of the next node, and then the output of the next node to the next node, etc., until we loop back to the first node. You can see here that each ring is actually following the NICs. And so NIC 1 from one node will communicate to NIC 1 from the next node, and all the NIC 1 will communicate together until we loop back, but we never go to NIC 2. And we have the same thing applying for each NIC, which means that we have some sort of rails for each NIC that operate independently. But because we split the data evenly on each rail, we need all of those flows to run at full speed and independently. And so this is quite important because we need to guarantee that all those flows will not cross each other or cause contentions with each other. For example, if they need to go to higher levels in switches and multiple flows end up using the same link, that could actually cause performance to go down. So that's usually why we also create a network topology that uses a different switch per NIC to make sure that all those flows will be actually going through independent pieces of hardware, and there will never be any risk of collision and interference. So rings work great, they get excellent performance, but they have a problem. Their latency is linear, which means that as you scale, the latency will become really high, and you won't get good performance unless you're doing operations on gigabytes of data, and if you don't, you only get a fraction of the bandwidth. And so that's why we also have trees inside Nickel. Trees have a logarithmic latency. They have a peak bandwidth which is similar to rings, but hopefully for small and medium messages, they can reach much higher bandwidth at smaller sizes. The principle of trees is not that different from rings. We will follow the same path pretty much intranode. And then internode will also follow the same notion of different rails where we split the communication on. And between the nodes, instead of just connecting nodes in a ring manner, we will do a tree. And we'll basically have the broad reduce first reduction operation that goes up the tree, and then a broadcast operation that goes down the tree. And if you're wondering what is this weird communication pattern that they use between the nodes, no need to zoom on that slide. I'll explain it right now on the next slide. So the way trees work is that for each NIC plane, we will create two binary trees and we'll perform a reduction up the tree and then broadcast down the tree. But to get full bandwidth, because one binary tree will be limited to half bandwidth because we have two flows going from the bottom and only one flow up. And so the two flows will create a bottleneck, which means we can only get half bandwidth. But there is a trick to actually get back to the full bandwidth. And the trick is to actually use two complementary trees, which have a very important property, which is that on one tree, all the nodes become leaves on the other tree and vice versa. So each node is a node on one tree and a leaf on the other. And that means that if you look at node 14, for example, here, we have two flows coming in and two flows coming out. And since we split half the data on one tree and half the data on the other tree, you basically have two flows at half speed coming in and 2 flows at half speed coming out, which means that the operation can actually run at full speed. Now again, this is only how we connect the nodes on the network side, but on the intranode side, we still have a chain of GPUs converging to one GPU per node, which is responsible for the internode tree communication. So in a system with 4 NICs, for example, we would have data converge to 8 different routes in the tree terms, and then coming back from those 8 routes down to all the GPUs. All right, so we finally created all rings, all the trees. Basically, nickel community rank is done now, and we can start running real communication, like all reduce, broadcast, or others. So whenever a communication operation is launched, so for example, when you call nickel or reduce, nickel will launch a CUDA kernel on the stream that is provided. And that CUDA kernel will actually communicate using the path that we have predefined before. And each path will actually be executed by 2 CUDA blocks, which means 2 GPU SMs. And they will have a continuous flow of data running through them. They will receive data from the previous GPUs defined in the rings or tree. They will do the reduction if needed with their local buffer, then write the results to their local buffer as well if needed, and then they will send data to the next GPUs in the tree or ring. And the pipelining is really of key importance here. Our goal is to really maintain a constant flow of small segments from the previous GPU to the next one, and that's how you can very quickly achieve good bandwidth. If you have 2 large chunks, you would actually get a very large overhead just to fill the tree or the ring. So this is really key here. The reason why we're executing on the SM is because we can have really fine-grained synchronization between the different GPUs that way, and that's really important to get maximum bandwidth. And if the previous or next GPUs are on a different node, then the CUDA kernel will just write data to a buffer that will end up actually being CPU memory, and there will be a CPU proxy thread that will just push that data to the next node through the network. And on the next node, we'll have another proxy thread receiving data and then notifying the local CUDA kernel that data is ready. And that local CUDA kernel will read from CPU memory without actually even knowing it. It will just do the exact same thing as if the previous GPU was on the same node. And if your network supports GPU direct RDMA, then we'll be able to send directly from the source GPU's memory through the network, and then receive directly to the receiver's GPU's memory. And that is especially important when the NIC and GPUs are connected through a PCI switch, because in that case, you definitely don't want to go back to the CPU. Otherwise, that would make the bandwidth much lower. And this is especially important on NVLink systems, which are usually designed to aggregate the bandwidth of multiple NICs. And it's only by making sure that all the traffic stays on the PCI switches that we can have that multiplicative effect, adding up all the bandwidth from all the NICs together. So that is all for all reduce and similar collective operations. Now, last year we announced that Nickel would soon be able to perform send-receive operations, and that has been first functional in Nickel 2.7, and then it's been optimized throughout the year through Nickel 2.8. So concretely, adding send-receive operations meant adding 2 new verbs, Nickel send and Nickel receive. Those are usually used together with Nickel group start and Nickel group end to form any send-receive communication pattern, be it like a bidirectional send-receive, a gather, a scatter, an all to all, neighbor collectives, and all their variations with different sizes per rank or different data types. It is very important to actually group those send receives if you ever want to guarantee that multiple send receive will be able to progress concurrently. And that is especially important because otherwise that could very easily create deadlocks, because otherwise if you have a send and then a receive, the receive will be blocked by the send. And if, for example, you have a send-receive operation, both the send and receive need the counterpart on the other GPU to be able to complete. So if you do send, then receive on both GPUs, both sends will be waiting for the receives to start on the other end, and that would never happen. And likewise, if you reverse the operations, the receive operations will wait for the send to start, and they will never start because they're blocked by the receive. So as I mentioned, all-to-all was really just functional in Nickel 2.7. It was actually even optimized for intranode, but for internode, it was really just functional. And in 2.8, we really wanted to make it fast. And to do that, we did two things. The first one was to increase the parallelism within the CUDA kernel so that we could do more send-receive operations concurrently. And now we can have up to 8 operations concurrently happening per CUDA block that we launch, which means that we can, depending on the number of channels, we can send and receive simultaneously to up to 128 other peers, other ranks. And that means that everything will be done at once. And if you have small messages, that's very important because you don't want to do one after the other. For the bandwidth side, it was also improved, as you can see, and the way to improve it was to just improve the scheduling so that we wouldn't, for example, just send to, if I'm GPU 0, I don't want to send to GPU 1, then 2, then 3, then 4, etc. Until the last one, because that would mean that for all the first steps, I'm always talking through NVLink, and there's nothing happening on the network. Whereas if I'm organizing the ranks slightly differently, combining far and near ranks, I'm always sure that there is always some network communication going on and some NVLink communication going on, and everything happens at once, and you never have any bubbles in your network where the NIC is pretty much doing nothing, or just receiving instead of sending and receiving all the time. So another case that we improved significantly in Nickel 2.8 is all-to-all for NVLink systems which do not have NVSwitch. And that is the case of the cube mesh in DGX1, where some GPUs have a direct NVLink connection, but some others don't. And for those, in Nickel 2.7, they would actually communicate through shared memory, which means that they will all use that path for a significant part of their communication, and that would be a very clear bottleneck. And the alternative to that is to actually use NVLink all the way. And it's actually not very hard. We just need to find a GPU that's between a pair of GPUs which are not connected directly through NVLink, and put the intermediate memory there on that intermediate GPU so that the sender can write directly to that memory and the receiver can read directly from that memory. And that way we move all the communication down back to NVLink, and as you can see, the bandwidth improvement is quite massive. More than 5x, which is not really surprising given that system memory is not really designed to achieve such high bandwidth. And that's it for Nickel 2.8. Now let's talk about Nickel 2.9, which adds support for CUDA graphs. So the idea is quite simple. We want to be able to capture Nickel operations as part of a CUDA graph, just like we would do for any other kernel that we launch on the GPU. And so capturing Nickel as part of the CUDA graph would start with a simple CUDA stream begin capture, which would create a CUDA graph object, and then capture everything that we launch between the CUDA stream begin capture and the CUDA stream end capture. And that is now what happens, as every call will be captured, be it a simple CUDA launch kernel or a Nickel launch, it will be captured as well. And if there's anything that we need to do in Nickel on the CPU side, we will make sure that we create the right work inside the CUDA graph to have operations happen on the CPU as well, for example, to progress the network operations. And then when we instantiate the graph, CUDA will create everything and run everything on the GPU, including Nickel, and in turn, the Nickel operation will also spawn the necessary CPU work if we are running between nodes. And moving on, let's now review what features are coming in the future, what we are exploring, and what we consider adding to Nickel in the next versions. So the first thing that we are exploring is the ability to leverage NVLink also for send-receive operations, so in particular for all-to-all, to try to minimize the inter-NIC communication that would have to go up the network layers. So that all the communication would stay as local as possible to the lower level switches and not cross too many hops. And as I mentioned, for rings and trees, we tend to design our networks so that all the same NICs from all the nodes connect to a different switch. So for example, all NICs 2 will connect to switch 2 and all NICs 0 to switch 0. And that's what we refer to as network rails, combining all the NICs, the same NIC across the nodes, plus a switch on the top. That's an independent communication channel for all nodes to use. And we know that traffic across NICs 2 will never impact the traffic across NICs 3 because they're just using completely separate hardware parts. Now for all-to-all, it's not like all reducer broadcast. It's not that easy because if GPU 0 has to send data to GPU 2 on another node, the easiest way is to just use the local NIC each time, but then that means that we'll land on different switches. And to communicate between those two, we'll have to go up the layers and down. And that can create contention because it could be that just different flows will use the same links at the top, and that could make one flow slower than the other. It could be that we also don't necessarily have an unblocking network, in which case there is a blocking factor, and that will obviously cause the bandwidth to be reduced. And so to avoid that problem, we have the solution to use NVLink. And just similarly to what we did for the intranode communication on the Cube mesh, we can do something similar here. First, move the data through NVLink to a GPU that is close to the NIC that is the same as the destination GPU. So for example here, if GPU 0 wants to talk to GPU 2, you would just have to push data to the GPU 2 on the same node, and then from there, initiate a network communication from that GPU 2 to the other GPU 2. And that would guarantee that all the traffic stays local to those leaf switches and never cross the rails and have to go to the upper levels. So the second thing we're looking at is to provide a Nickel average operation. This should allow to skip the fusion plus scaling step that is usually done before Nickel and even after. And instead of fusing the buffers into a single big buffer and at the same time scaling it down, dividing by the number of ranks on the group, you would just have to launch Nickel with multiple or reduce operation, for example, all part of the same group, and using the Nickel average operation instead of the Nickel sum. And that should make the code simpler and hopefully faster as well, because we're just removing 2 extra steps. And finally, a few things that we've been looking at for the next versions, small things. First, we have support for bfloat16, which is a data type that is increasingly being used in deep learning. We've been asked to add a new function to retrieve the last error that Nickel reported. Usually that's the error you see when you set Nickel debug equals 1 to have a human readable message that tells you what went wrong. But sometimes deep learning frameworks want to actually report that themselves to make the reporting to the user better. So that's a function that we're looking to add. We're also trying to improve our fault tolerance. As I mentioned, we have functions to find errors, detect errors, and then stop everything. But we still have a few corner cases where, for example, if an error happens during initialization or or even during destroy, we could have issues where we are not able to actually abort that operation and recover from there. And finally, last but not least, it is always our priority number one to make sure we continue to provide the best performance on all platforms. All right, summarizing. Nickel is an inter-GPU communication library for CUDA applications and used by all deep learning frameworks to accelerate training on multiple GPUs. It is optimized for DGX, OEM, cloud, or even your laptop or desktop. It is designed to be easy to integrate into any parallel program, being using NPI or not, and it only depends on CUDA. And that's all for this talk. I hope it clarified what Nickel is and why it's an important component for multi-GPU computing. If you have any other question or want to discuss problems more in detail, feel free to check the Connect with the Expert sessions, which are related to Nickel. One is on multi-GPU computing with CUDA, and the other is more focused on deep learning, training, and scaling. Thank you.